Okay, good afternoon, everyone. Sorry, the technical difficulties just encountered. So today I will talk about advanced packaging platform and a design case for chiplets integration in HPC application. This is kind of an outline for today's discussion. So I will start with the introduction and talk about advanced packaging technology for chiplets and heterogeneous integration. Then I will introduce ASE advanced high-density fan-out solutions, following by some process flow and also risk assessment. Then I will introduce ASE advanced high-density fan-out design case. Finally, summarize the conclusion. So we already see the digital transformation has encompassed our daily life, and from Internet of Things to Internet of Everything, automations, and also AI machine learning. And based on the Prismark analysis report, by 2024, and the PC, mobile, and also the server storage infrastructure will still the key dominators to make the semiconductor growth significantly. So among this, and server storage communication will become the fastest growth with a CAGR about 8.1%, and following by automotive growth as the second fastest segments. So let's look at the advanced packaging, the trend, and also the performance requirement. So the first chart here shows the Moore's law is slowing down. Everyone talk about this. So if you look at the number of transistors keep increasing, however, the performance, especially the single thread performance, has reached the plateau. And also the frequency has flattened, and especially the power of chips got constrained. So if you look at the cost for silicon node development, you can see this chart is increasing significantly, especially for small silicon node, such as 7 nanometer, 5 nanometer, down to 3 nanometer. So most importantly, people ask the high performance. So for example, the I/O, the bandwidth doubling every 3 months, but not stop here. The most important, people talk about the power. The off I/O takes too much power. That's why the total I/O power will exceed the package can supply. So what does that mean? So that all request the new innovation for the advanced packaging, for the new integration. That's why the chiplets and heterogeneous integration become the key enablers. Because of their unique advantage, they allow the disaggregation of SoC from monolithic to the modularized. And not stop there, because they also can reuse IPs and can leverage the performance and also can short the time to market. So that's why it gave the low cost. So chiplets and heterogeneous integration also drive the advanced packaging technology development. So we have seen the new breakthrough have been happening in the market right now. For example, people talk about the flip chip BGA, but it's beyond that at 2.5D silicon TSV for the integration technology, and also the fan-out RDL, and down up to the 3D micro bump provide very high density die-to-die interconnect. So ASE, we are as advanced packaging provider. We're offering turnkey solution and with the covering wide portfolios. For example, from the wire bond to flip chip to wafer level packaging. And lately, in this year, we announced our vertical integration package we call the VI-Pack platform. So today, I will focusing on 3 key VI-Pack technology for chiplets integration. So here, just show some example. This is the 2 very key platform. We call the fan-out on substrate. We have a chip first, we have a chip last. The key features for these two platforms, basically, it allows the disaggregation of SoC, especially it provides very high density between die-to-die interface, with the line spacing interconnect down to 2 by 2 micron. And it can serve for the HPC application. For example, APU, GPU, AP integration with HBM over your DRAM memories. It also can provide for the networking increasing applications and for SerDes integration and also for AI machine learning definitely. So another key platform, compare this fan-out pure RDL platform. We also have the high-density fan-out silicon bridge technology. So compare these two. Silicon bridge technology, the bridge is a silicon bridge, can connect die-to-die interconnect. But the beauty of this technology is it can provide a super high-density die-to-die interconnect. So the line spacing can down to 1 by 1 micron, even lower, such kind of 0.65 by 0.65 microns. So this technology also can give them more flexibility on design, especially on the performance combinations. So I will basically give a very high level the process flow at each platform. So this flow chart just shows the chip first. What does mean the chip first packaging process? So basically, the chip first, you put the ASIC die or chiplets first on the carrier. After that, you use a molding material to cover it. After the covering, and you remove the carrier, and then you start to build up your RDL layer. And after RDL layer build up, and you can do the bumping, and after that, you can put on the substrate. So the key point is you put your chiplets first. As a contrast, chip last. So chip last means we do the RDL on the carrier first. After you completed the RDL, and you do the bumping, and you put your chiplets on the RDL. And after that, you definitely dicing and singulation, and you become the fan-out module, and you put on the substrate by the conventional flip chip process. So you look at these two, the differences, key differences depend on where you put your chiplets. If you put first, we call chip first. If you put last, chip last. So chip last basically compare chip first, give you the good advantage because you can avoid your non-good die loss. So if you integrated HBM, for example, you need to go to chip last because HBM has the thermal budget requirement. So you put the last, you're not going through the thermal cycle when you do the RDL. So if you look at the bridge, so the basically bridge, compare these two. So we put the bridge, smaller bridge die between the two chiplets over a few chiplets. So this bridge die inside, there is a very high, very fine line spacing and a high density of interconnect. So the line spacing can down to 0.6 below. So compare these two, or these three. The bridge gives you more flexibility for your die-to-die interconnect. So this is give some example by using the 3K platform and what's the TVs we build up. Now some TV already in mass production. For example, so this is the chip first. We integrated the two ASIC die. And the die-to-die interconnect, we're using the line spacing 2 by 2. And you look at the die size, actually the total fan-out size is 30 by 28. The package body size is 47.5 by 47.5 millimeters square. And you look at the focus chip last. This is the sample we show you is integrated with 2 HBMs, 1 ASIC with 2 HBM. And the body size, the substrate body size is the same as the chip first, and also the die-to-die interconnect. We use the line spacing 2 by 2 and the total 4 RDL routing plus 2 metal layers for the pad connection, so total 6 metal layers. And you look at this is the bridge. So in this sample, it shows you we have 2 ASIC die, total 8 HBM. and put on the very large package body size with a 78 by 70 millimeter square. And you look at the count, the chiplets is a total, the 10 chiplets, and the total 8 embedded die to connect between the ASIC and HBM. So this is a chart just to show you that all this the platform and the TVs pass the standard JEDEC reliability test. So, but this is the last but not least for today's talk. I just show you the high density fan-out technology, the design case. So as you know, and standard package design is very known. So for example, this just show you the substrate design case. It's normally we use the cadence APD file and generated the Gerber file, and you can route it. But how about the high density RDL design? So this is at the top, just to show you the RDL design flow. So basically we use the IC design tool to do the auto router for RDL. And after that, we also leverage the package design tool, the APD file, and to optimize your RDL design. After that, generated the GDS file. Then use the GDS file, you can do the LVS or DRC, the design rule check. So finally, you will generate the mask, your RDL mask design. So on this, we also use the auto mask design tool to generate it. So this, our design case can really improve our layout cycle time 50% by use of auto router. And also we can provide ASE, the packaging design case, and for the RDL design can work with IDM and the system house to use this advanced packaging platform for chiplets integration. So I'm quickly down to my summary for today. So basically, the key message we want to deliver is chiplets and heterogeneous integration and really can optimize the system performance. And as the provider, we really can provide multiple the platform to fulfill the chiplets integration and also to optimize the performance. And that's what this is the key delivery message I want to deliver here. And thank you, everyone. If you have any questions, and please let me know. Thank you.
Thank you, Lihong. Questions?
Thanks for the presentation. So yes. One question I have is, why would anybody offer, why would you offer a chip-first process when the chip-last process has several advantages?
Well, that's a very good question, yes. So why we want to offer? So basically, the chip-first can provide, compare the performance-wise, is a little bit higher performance because chiplets, first, I don't have the micro bump in between. So my die can make the short link to the RDL. But the chiplets, I have to use between the die and RDL, I have used the micro bump. So this is the one region. Second region, if you talk about the pitch reduction, so if you want to do the pitch reduction by using micro bump, so currently the smallest micro bump pitch, as everyone knows, is a 55 to 40, for example. And the 35 is studied under development right now. But the chiplet first, you don't need micro bump. That's why your die-to-die bump pitch can be reduced to 20 or 25 microns. So this is the key. And if you choose which one, so it depends on your performance requirement and also depends on how much tolerance your design can give. Yep.
How do you attach the die on the chip first to the package? How do you attach the die to the package using the chip first process?
Okay, yes. So the die, so first, incoming die, and first you have to dicing, and you become the singulation, and you put the die on the carrier. We have the carrier. You put the die on the carrier. So this process we call the reconstitution. So after that, and you molding. So after molding, you remove the carrier. So this time, and you flip over, then you do the RDL plating. So this is how you put the die. Yeah, thank you.